Okay. So I'm going to be talking about supermodular games, which are an example of a combinatoric game. So the strategies are not continuous variables in these games necessarily, but they can take arbitrary values in some set. And in fact, the set that these strategies take place has a certain special structure. And so the history is Topkiss in the late 70s. He introduced submodular games, and he applied these games to certain aspects of economics. And then in 1991, Joe wrote a paper that I'm basically giving this talk off of that paper. And the paper itself is very technical. It's also short but technical, but I'm trying to not be nearly as technical as the paper, and I'll skip a lot of details. But before we can define submodular games in their, not submodular, sorry, supermodular. Of course, there are things called submodular games that are essentially just the dual version. Instead of payoffs, you have costs, but for our purposes, we can focus on supermodular games. So we need a little bit of lattice theory. And why do we need lattices? They allow us to define supermodular games in their full generality. So many people I've talked to at Grasp Lab are not necessarily familiar with lattices. It's a very useful notion that can be very useful in engineering, but it's not well known, and it sort of has this niche community in mathematics, and also quite a few economists know about it, but not so many engineers. But the concepts behind lattices are very familiar. You start with a partially ordered set, which is a set with a binary relation. And we can think of this relation as a notion of preference. And by the way, if anyone can't read my handwriting, I can rewrite something or say what I mean. So this relation satisfies three properties. And let me get my little laser pointer. The first property is symmetry. So an element of the set is related to itself. Then we have what is really called anti-symmetry, where if x is less than y, less than or equal to y, and y is less than or equal to z, then we have that x and y are actually the same element. And then the third property is transitivity, which states what is below, that if x is less than or equal to y and y is less than or equal to z, then x is indeed less than or equal to z. So my example for my two favorite foods that are prominent in the region are pizza and cheesesteaks. I do like pizza a lot, but I prefer cheesesteaks over pizza. So preferences really fall naturally into the notion of a partial order. And of course, there's preferences or priorities common in engineering applications. For example, a bunch of tasks that a robot needs to complete, they might be ordered in a partial order. But one thing to keep in mind with partially ordered sets is that they are not totally ordered, meaning that two items in a partial order might not be comparable. There may not be, you may not prefer, cheesesteaks to Chinese, or Chinese to cheesesteaks, but you might prefer cheesesteaks to pizza, for example. So here we have a notion of a lattice, which is a special kind of partially ordered set. It's a partially ordered set such that for any two elements in the set, we have a least upper bound called the sup of those elements and a greatest lower bound, also known as the inf. And this is our notation for least upper bound, and this is our notation for greatest lower bound. And this notation is kind of confusing. So in order to be a lattice, we have to be a partially ordered set, and we have to have these binary, this is called a join, the V symbol, and then we have a meet, which is the wedge symbol. So we require that these two things exist. And so there's many examples of lattices. Our first example is a power set of some set. So we have a set of things, and we consider all possible subsets of this global set. And we have that the meet operation is the same as the intersection of sets, and the join operation is the same as the union of sets. So whenever you're confused about which one is the meet and which one is the join, we just look at this analogy between the intersection in the meet and the join and the union. Another example, which is probably my favorite example, is you can consider a vector space, for example, Rn, then all the linear subspaces of this vector space form a lattice. The least upper bound in this situation is the vector space sum. So we take the sum of all linear combinations of vectors from W and from U. And then the meet in this lattice is the intersection. A third example, this should say 3, consider the real numbers, vectors n tuples with a product order, meaning that this vector is less than or equal to that vector if every component is less than or equal to the component of the right-hand vector. And so here we have meets being the component-wise minimum of these two vectors, and joins being the component-wise maximum of these two vectors. And another definition we'll need to prove something about the Nash equilibria of supermodular games is the notion of a complete lattice, which is a lattice in which you not only have binary meets and joins, but you also have any arbitrary subset has a greatest lower bound and a least upper bound. And this, of course, includes the empty set. And if you think about it, the least upper bound of the empty set is going to be the smallest element of the lattice. And the greatest lower bound of the empty set is going to be the largest element of the lattice. And we also consider functions between post sets and lattices, and they are distinguished by preserving the structure of either a post set or a lattice. So for example, a monotone function satisfies this property, meaning that whenever you have something that is less than another thing and you apply f to these things, you'll get this order property that's still preserved. And in the case of lattices, I guess we don't actually end up using this in this talk, but the important maps of interest are join preserving maps and meet preserving maps. The second part of the talk, I'm going to state a result called the Tarski fixed point theorem, which is due to a Polish mathematician in the early to mid 1900s, named Alfred Tarski. Some notation here is we can consider a monotone function, and then we have what are called the prefix points of this monotone function. So remember, this function is order preserving, and it also, the domain and the range or codomain of this function are the same. So we consider the prefix points of this function are all the points so that when we hit them with f, we're less than or equal to where we started. And then, of course, we have the post f, or the suffix points, which is the opposite of this notion. And then if we take the intersection of the prefix points and the suffix points, we get the fixed points, which there are a lot of fixed point theorems out there. For example, the Banach fixed point theorem. In analysis, you would encounter. But this is a purely combinatorial fixed point theorem. And it states that if you have a monotone function on L, which is a complete lattice, so we have joins and meets everywhere, then the fixed point set is also a complete lattice. So there's a proof of this in one of my papers, but I'm just going to go over the proof here. So what we have to show is that if we have any subset of the fixed points of F, that subset has to have a least upper bound and a greatest lower bound that, of course, they exist because they're in L, which is a complete lattice, but they must be contained in the fixed points. So suppose we have a subset of the prefix points of F and any given element of that subset, then we have this inequality by the order preserving property of F, and by the fact that we assumed X was in S, which is also in prefix, so it satisfies this property. So this implies that this is in the prefix points. And it turns out for complete lattices, you can write least upper bounds or joins. You can always write them as meets of a different set. And these exist because we have arbitrary meets. So we also have the join of S's in our prefix points. But this is not what we were trying to show. We're trying to show that the meets and joins of subsets in the fixed points of F are also in the fixed points of F. But this isn't much of a difficulty because a similar argument will show that the suffix points of F is also a complete lattice. And then we can write the fixed points of F as the suffix points of F restricted to the prefix points of F. So this is just a trick, essentially. And then you get that the fixed point is complete. So that's what we wanted. Section 3, this is a short section. I'm going to define what a supermodular function is. So we have a function from L, a lattice. And remember, our lattices can be very familiar. For example, Euclidean space Rn with the pointwise max and pointwise min is an example of a lattice. And in some definitions, in some textbooks, you'll see supermodular games and supermodular functions just defined for this specific case of Rn with pointwise min and max. But more generally, a supermodular function is a map like this that satisfies this property. And you can think of this property as a notion of inclusion-exclusion that's sort of abstracted to this lattice theoretic perspective. Except for inclusion-exclusion doesn't hold on the nose, and you actually have an inequality. So if it did satisfy inclusion-exclusion, then we would actually have an equality here and not an inequality. So this property is important in optimization, although usually presented as a submodular function, and you're trying to minimize cost, but you could just as easily have a supermodular function and trying to maximize a reward, or maybe it's the opposite, I can't recall. So here's what a supermodular function is. Okay, now to jump to really the point of this talk, I want to define supermodular games. And even though they seem quite abstract, there's several applications in engineering and many in economics, but some in engineering. And one example I liked is for wireless network power control. And there's a paper right here that appeared in 2003 in the IEEE Transactions on Automated Control. And the idea in this game is that the users, the players of the game are users that want to use a common radio channel. And the game is to compete with the other users in order to maximize the signal to noise interference ratio. That is to avoid interference with other users. And the dial you can turn here for this particular paper is you can adjust the power levels of your transmissions. And of course, there's probably constraints. For example, your power level has to be greater than whatever in order to successfully transmit. And there's also constraints that you can only generate so much power given the hardware involved in your transmission. But under these constraints, you can pose this as a supermodular game. So what is a supermodular game? It consists of players, as any game does, and actions, as any game with complete information that we know the possible actions, or another word for actions is strategies, of every other player in the game. And here, what makes this different than any old game is that these AI, or sets of possible actions that agent I can take, is a complete lattice. And in turn, this means that if we take the Cartesian product of all these possible strategies for every agent, this Cartesian product is also a complete lattice. And this is called the A, without any subscript, is called the action profile. So as in any other game, we have a utility function, UI, from the action profile that given a strategy that I have, which is the A sub I, and the sub strategies of everyone else, which our notation, which is very common, is the A sub minus I. So it's everybody, all the agents except for me. So we assume that this U sub I is a supermodular function in AI, which means that if we fix a minus I, then this function is supermodular. We also make this assumption that UI satisfies increasing differences, which means that if you have a strategy AI and a strategy BI, and then everyone else has a strategy S minus I and T minus I, that we have this following inequality. And the way to think about this is we fix our own strategy here, and then we take a strategy that's greater than this strategy. So our utilities are going to be positive. Well, actually, we don't know that they're going to be positive because we make no assumption that this UI is monotone. But this increasing differences is kind of a weaker notion than saying, hey, if I have this strategy and then if we have this strategy, that this difference is going to be positive. We actually don't know that, but we know by assumption that we have this inequality that if we fix these BIs and then have this T minus I that's greater than this S minus I, and likewise, if we fix AI, which is smaller, and I think the A's and B's should be swapped. I think that's an error, but I'll have to double check that. But anyway, yeah.
Yeah, is this a property also for the submodular functions of the increasing differences?
No, so this is, well, a good point. Okay. I'm pretty sure that if you have a submodular function and you assume that this function is monotone, meaning that then you get this increasing differences property.
Yeah.
Okay. But this is a little bit weaker, and in retrospect, I should have figured this out beforehand and maybe just presented this in a little bit of a cleaner way by not using this property. But in this paper that I'm going off of, they use this property of increasing differences.
All right, thanks.
Yeah, no problem.
Also, this looks like decreasing differences, like maybe AI and BI should be interchanged.
Yeah, I think they should be. I think that's an error in my notes that I made up this morning. But anyhow, the main result that I want to present, and usually in game theory, one thing that you care about, and maybe the main thing you care about, is you define a certain game, and then you want to ask, what are its Nash equilibrium? Maybe, I don't know what they are, but maybe there's an algorithm to find them. Maybe I can say something qualitative about the Nash equilibrium. So maybe there's just one, maybe there's infinitely many, etc. So we're going to say something like that for supermodular games. And so just as a recap, I just want to remind everyone that a Nash equilibrium is a particular strategy A such that for all B, I, which are alternate strategies that I could have, that we have greater utility when we fix the strategies of everyone else besides me. And of course, this has to be true for all players of the game. So this is a pure Nash equilibrium. For a Nash equilibrium, we have this whole business that Kyle talked about a little bit a couple seminars ago, where we have we care about like expectation, and our strategies are do this with probability blah, do that with probability blah blah. But in this case, everything is kind of discrete, and we don't really have mixed strategies. Maybe you can extend this work to mixed strategies. Maybe you can't. I don't know. But our main theorem here is due to Joe, and it's that the set of Nash equilibrium of and of course we're assuming perfect information, of a supermodular game is a complete lattice. And the implication of this in particular, one implication, is that there is a maximum strategy, maximum Nash equilibrium, and there's a minimum Nash equilibrium. And any two strategies that are a Nash equilibrium have a least upper bound and a greatest lower bound. So this gives us this nice way of moving between Nash equilibrium and understanding the underlying structure of what these equilibrium are in our game. And this theorem is in the paper, which just the title of the paper is just saying what the paper does, but it was in Games in Economic Behavior, published in 1991. And this journal is really big in game theory, probably the most important journal in game theory. So going to review some more definitions. The best response, which I call BR, is a function from the action profile A to the action profile. And basically what this function does, component-wise, is it says the best response for agent I, given their strategy and the strategy of everyone else, is this argmax. So you minimize, you don't minimize. You take the utility or the strategy that maximizes your utility. But remember, even though this isn't really in this component, it's not a function of AI, because AI is something that you maximize over. It is in fact a function of the other strategies, and so each component is not like separable, that you have to maximize over all these different things. And one thing to note is that given the structure of these utility functions, that you may not have a single argmax, that you might have multiple strategies that maximize utility. So really this best response is a function that takes you from the strategy profile of the entire game to the power set, so all subsets of the strategy profile. But this is kind of a subtle point, and you can sort of assume that this BR function is actually from A to A. If you assume that these utilities are what you would call single peaked, or what an economist would call single peaked, but what anyone else would probably just say has a single global maximum. And so how does this this thing connect to the Tarski fixed point theorem? Well, it turns out that you can say a strategy A is a Nash equilibrium if and only if it's a fixed point of the best response function. So this kind of gives you a sketch of the proof. And there is a notion of being a fixed point, for example, if you don't have a monotone function from A to A, but it's actually from A to the power set of A. And that's just saying it's the set of A such that A is an element, and not equal to, but is an element of the best response of itself. So just a sketch of the proof of the main theorem. What you need is actually a generalized version of the Tarski fixed point theorem for maps like this. And this is kind of why the paper I mentioned is very technical, but they do prove that theorem, and you end up having to show this property called ascending property, which you have to show for all A less than B. So this is a strategy A and a strategy B. And for all B prime that are a possible best response for strategies B and strategies A, then you have to show that their join is in BR of B and their meet is in BR of A. So you can show this by applying supermodularity of the utility functions and this increasing differences property, and you get what you want. So yeah, that's the thing. That's all I have. I went a little bit faster just in the, since there's not too many people, and I hope we could go back and maybe clarify some things since I ended so abruptly.
Yeah, thank you very much. It was great. Like I'm very new to this, so I have to like read up more before I can ask.
All right.
Yeah.
So in reading for this thing, I had like an idea of something like we could all read. But maybe I'll end up posting about this, and then we'll see if this is something good to read. But there's this new textbook called Cooperative and Graph Signal Processing that's really good, and it has a chapter on game theoretic learning. And I probably can share